Hello there, and welcome to the Sleepless Scientist, a quiet corner of the cosmos where curiosity finds rest, and the vastness of knowledge becomes a gentle lullaby for the night. Tonight, our journey drifts through the wide fabric of the universe and into the quiet heart of one timeless question. What is the most powerful force in existence? Is it gravity, pulling stars and galaxies into their grand cosmic dance? Is it the electromagnetic field, weaving light through every atom? Or could it be something softer, the force that binds life, thought, and wonder together across the emptiness? Tonight we'll follow each thread and listen for the quiet truth beneath them all. But before we begin, I'd love if you could take a moment to like this video and subscribe. Only if these calm explorations bring you peace. And when you're ready, leave a comment to tell me where in the world you're listening from and what time it is for you right now. It's always a small joy to see this constellation of listeners scattered across different hours, yet gathered here in the same moment. Now dim the lights. Maybe let the soft hum of a fan or the rhythm of your breathing be your background. And if your thoughts begin to wander, let them. That's part of the journey too. We'll still be here, quietly unfolding the story, one gentle force at a time. Tonight's question isn't one with a simple, singular answer. It doesn't ask, what's the loudest thing? Or what explodes the brightest? But something a little more thoughtful. It invites you to think about power, not as domination or noise, but as change, as transformation, as influence over time. When we hear the word power, we often think of energy, big bursts of it, crashing into our senses, explosions in space, hurricanes on Earth, engines roaring to life. But power can also be quiet. It can whisper. A black hole doesn't scream its strength. It simply bends the space around it until nothing can escape. A single mutation in a strand of DNA invisible to the eye can reshape a species. And somewhere, in the back of your mind, a dream might rearrange how you feel about your life, without anyone noticing. So tonight, we'll travel through a series of forces and phenomena, from the smallest building blocks of matter to the grandest scales of the cosmos. We'll pass through the intense embrace of the strong nuclear force, drift alongside collapsing stars that scream one last time into the dark and slip quietly past the event horizons of black holes. We'll meet strange companions along the way, dark energy, dark matter, quantum fields, and the peculiar miracle of consciousness. And slowly, gently, we'll consider what it really means for something to be the most powerful. To begin, we have to know what science actually means when it talks about a force. In physics, a force is simply any interaction that changes the motion of an object. That might sound dry, but it covers almost everything. Every push, pull, twist and ripple across space and time. And according to our best understanding, all the complex interactions in the universe can be traced back to just 4 fundamental forces. Only 4, that's it. Out of all the chaos and complexity of the cosmos, 4 forces guide the dance of galaxies and atoms, alike. Like 4 instruments in an invisible orchestra, they play at different volumes and scales, but they are always there, shaping everything. We'll explore them soon. For now, just let that sink in. Behind every heartbeat, every falling leaf, every ray of sunlight crossing the void, there is structure, there is pattern. There is a kind of quiet logic humming beneath reality. But these 4 forces, as mighty as they are, don't always reveal themselves equally. Some are subtle, some are short-ranged. Some only show up under extraordinary conditions, inside the cores of stars or within the heart of a supernova. Others are around you all the time, pulling you gently toward the ground, holding your coffee in your cup, guiding the electrons in your brain as you listen to this. You may be wondering, if we already know what the strongest force is, why ask the question at all? Couldn't we just say the strong nuclear force and go to bed? Well, Perhaps. But that wouldn't tell the whole story. Because strength isn't everything. Endurance matters too. Influence matters. What lasts, what spreads, what reshapes the future long after the event has passed. That too is a kind of power. And so we begin with curiosity, not the kind that jolts you awake, but the kind that lets your thoughts meander like a stream under moonlight. What makes something powerful? Is it energy, speed, scale, or is it something softer, like the ability to change minds, to create meaning, or to endure in memory? The universe doesn't answer such questions outright. It gives us glimpses, a flash of gamma rays from across the cosmos, a soft gravitational lens stretching light like taffy around a cluster of dark matter, a pattern of waves in the cosmic microwave background, still echoing from the moment time itself began, a heartbeat, a thought, a tear, a choice, and through all of it, something is at work, pulling, pushing, organising, unravelling and becoming again. So, we begin, slowly, quietly, from the very forces that hold the smallest things together to the ones that bend the fabric of reality itself. And in the end, maybe, we'll arrive not at a final answer, but at something better, an understanding as soft as a whisper about the nature of strength itself. Now, close your eyes if you'd like. There's no need to follow every word. Just let the story move through you like a breeze. We'll start our first real step with the forces that make everything possible, and one of them, though you've never felt it directly, might be the strongest thing you'll never see. Let's imagine just for a moment that you could press pause on the entire universe. Not stop time completely, but freeze the motion of everything, every falling leaf, every orbiting moon, every vibrating atom held perfectly still in the dark. And now, in that stillness, imagine you could see all the invisible hands that were holding it all together. Not strings or scaffolding, but something more subtle, more fundamental. You'd see 4 of them, 4 great forces, not armies or explosions or roaring winds, but quiet influences that shape the behaviour of all things, from the smallest specks of matter to the swirling arms of galaxies. In the language of physics, these are known as the 4 fundamental forces: gravity, electromagnetism, the strong nuclear force and the weak nuclear force. And astonishingly, everything we've ever observed, from how atoms form, to how stars burn, to how your fingers feel warm under a blanket, can be traced back to just these 4. It's a little like hearing a symphony and realising that it's built from only 4 instruments, each with its own tone, its own range, its own rhythm, but always playing together, always weaving through the silence to make something far more intricate than anyone could on its own. Let's meet them, gently, slowly, one by one. The first is the one you probably know best: gravity. It's the soft, persistent pull that keeps your feet on the floor, the moon in orbit, and the Earth tracing a lazy ellipse around the sun. Gravity is the reason raindrops fall, tides rise, and galaxies hold their stars in vast rotating spirals. It's familiar, it's comforting. But what's surprising is just how weak it actually is. On small scales, it's the least powerful of the 4. If you don't believe me, consider this. Lift a paperclip off your desk with a small magnet. In that moment, the electromagnetic force in that tiny magnet overcomes the entire gravitational pull of the Earth below it. That's the second of our 4 forces, electromagnetism, and it's a shapeshifter. It governs light, electricity, magnetism, and chemistry. It's the reason your lamp glows, your brain fires signals, and your skin can feel the breeze. Unlike gravity, which only attracts, electromagnetism can both pull and push. And it works at the level of atoms and molecules, which is why it defines so much of the texture of daily life. Then we move inward, much deeper, into the nucleus of the atom, where we find forces that are not just strong, but strangely strong. The strong nuclear force is, as the name suggests, the mightiest of them all. It binds protons and neutrons together in the heart of atoms, overcoming the fact that protons, being positively charged, should violently repel one another. But they don't, because this force glues them in place, tighter than anything else in nature. It doesn't reach far. In fact, it only works at subatomic distances, smaller than the width of a single proton. But within that tiny space, it reigns supreme. And finally, there's the weak nuclear force, perhaps the most shy of the four. You don't feel it, you don't notice it, but it's quietly at work behind the scenes, enabling one type of particle to turn into another. This is the force responsible for radioactive decay, for the transmutation of elements in stars, and for the steady fusion that makes the sun shine. The weak force is less about binding and more about changing, about transition. In a way, it governs transformation, and while its name suggests frailty, its consequences are enormous. So there they are, the four threads. One holds everything down, one dances through our senses, one binds the tiniest things with unmatched intensity, and one whispers the instructions for change. Each has its role, each has its time, and together they form the scaffolding of reality. But they are not equal, not in strength, not in range, and not in how often they appear in our lives. Gravity acts across vast distances, and though it's the weakest, it never turns off. Electromagnetism is powerful and versatile, but it's easily cancelled out. Positive and negative charges often balance one another, making its effects less obvious in neutral matter. The strong force is intense, but it can't reach beyond the core of an atom. And the weak force is even shorter in range, operating in the quiet drama of particle decay. Scientists sometimes organise them into a kind of strength ladder. From strongest to weakest, the strong nuclear force, electromagnetism, the weak nuclear force, and finally, gravity at the bottom. But weakness is a tricky word, because while gravity might be weakest in direct force, it's the architect of galaxies, the shaper of time itself. And while the strong force is mighty, it's limited to spaces far smaller than you could ever see. The universe, it turns out, doesn't measure power in a single dimension. A force can be powerful in one moment and absent the next. It can act briefly but profoundly, or gently but constantly. What matters isn't just strength, it's context, its purpose, its consequence. So perhaps it's better to think of them not as competitors, but as collaborators, like a team of dancers in an invisible performance, each with their own move, their own tempo, weaving together the act of existence. And as we continue, we'll look more closely at each of these forces, starting with the strong nuclear force, whose grip is so intense it never lets go. Even when we try to pull it apart, it only responds by creating more of itself. But that's for the next session. For now, just rest in the quiet wonder that the whole universe, all its complexity and beauty, arises from just 4 types of invisible threads. If you were to shrink down far beyond what your eyes can see, past skin, cells and molecules, into the very heart of matter itself, you would find something unexpected. Not a smooth surface, not even a compact ball, but a storm. A swirling chaos of particles darting and tugging at one another in a dance so intense, so tightly woven, that if you tried to pull them apart, the universe would respond by making more. This is the realm of the strong nuclear force. At the centre of every atom lies a nucleus, tiny, dense, and incredibly powerful. Inside that nucleus are protons and neutrons, and inside those are even smaller particles called quarks. But quarks don't exist alone. You'll never find one wandering by itself. No matter how hard we try, no particle collider, no explosion. No force in our technological reach has ever been able to isolate a single quark. Instead, if we try to pull two quarks apart, the energy we use doesn't break them apart. It simply creates two more quarks to bind with the originals. It's as if the universe refuses to let them go. This behaviour is a direct result of the strong force. It's not just powerful, it's clingy. It acts like a kind of cosmic superglue, holding quarks together so fiercely that they can only exist in groups. And the messengers of this force, called gluons, live up to their name. They're constantly being exchanged between quarks, like sticky notes flying back and forth, reinforcing the bond. But the strong force doesn't just bind quarks, it also holds protons and neutrons together inside atomic nuclei. And this is no small feat. Protons, remember, all carry a positive electric charge, and like charges repel. So inside the nucleus of every atom, there's a silent battle. The electromagnetic force is trying to push protons apart, while the strong force is clenching them tightly together, and it wins. It always wins, at least within the scale of the nucleus. Without this force, atoms would fly apart, matter would dissolve, and the universe as we know it would vanish. It's hard to imagine how much energy is packed into that small space, but we get a glimpse of it in nuclear reactions, when the strong force is overcome, or rather, when we trick it into rearranging. Vast amounts of energy are released. This is the principle behind nuclear fusion, the process that powers stars. In the cores of stars, hydrogen atoms are crushed together under immense pressure, fusing into helium and releasing energy in the process. That light, the one that warms your face on a sunny day, began as a product of the strong force yielding to change. And yet, for all its might, the strong force has an extremely short reach. It only acts at distances about the size of a proton. Anything beyond that, and it fades almost instantly. It's like a hug so powerful that it cannot be given at arm's length. You have to be right there, impossibly close, for it to work. But once inside its embrace, you're held with a grip no other force can match. Scientists call this phenomenon confinement. It means that quarks are forever locked into groups, either in threes, which make up protons and neutrons, or in quark-antiquark pairs. You might picture quarks as tiny dancers tethered by cords that stretch but never break. And if you pull too hard on those cords, you don't break them. You snap the vacuum itself, and the universe pops new quarks into existence to repair the bond. It's a strange kind of generosity. The more you try to separate, the more the universe insists on togetherness. And then there's another curious behaviour. Unlike the electromagnetic force, which gets weaker the farther apart things are, the strong force does the opposite. The farther you pull quarks from one another, the more the strong force resists. It's like stretching a rubber band that never loosens, only tightens. There's no letting go, no escape, only the promise of resistance and eventually creation. This behaviour, while mathematically elegant, also speaks to something strangely poetic. That at the heart of matter lies not separation, but union. Not release, but bond. Even the very act of pulling things apart doesn't lead to isolation. It leads to more relationship, more interaction, more togetherness. In a way, the strong force feels like a guardian of integrity. It doesn't just keep particles together, it defines their identity. Without it, quarks wouldn't be quarks in any meaningful way. Protons would not exist, atoms would not cohere, and the energy that shapes the stars and your own body would never have formed. You might think of it the next time you hold something small and solid in your hand. A coin, a grain of rice, a pebble from the ground. Inside that object are countless particles locked in place by this force. Their existence is quiet, invisible and constant, but without it nothing would hold. And still, we rarely think about it. Because we never feel it directly. It doesn't act on the scale of your body or even your skin. But it's there, in everything. Every breath you take is made possible, because this hidden force is still working, still binding, still whispering, stay together. As we move forward, we'll zoom back out from the inner tightness of the strong nuclear force to the vast openness of space. And there, we'll meet a force that's not strong at all, at least not in the usual sense, but whose reach is eternal, whose influence is global, and whose quiet pull guides the dance of galaxies. But for now, just know this. At the heart of everything solid, everything real, there is a kind of invisible glue, not seen, not heard, but always, always holding on. We've just spent time at the heart of the atom, where the strongest force in the universe holds matter together so tightly it refuses to let go. But now, let's step away from the intensity of the microscopic. Let's move slowly outward, past the nucleus, past the cell, past your room and your street and your sky, and into the great open spaces between the stars. Out here, the rules begin to shift, and one force, so faint it was once thought unremarkable, begins to assert itself as the quiet ruler of everything. This is the realm of gravity. Gravity is the most familiar of the four fundamental forces. You experience it every day, though perhaps without truly noticing. You feel it in the gentle tug that keeps your feet planted on the floor, in the way your tea always settles to the bottom of the cup, in the pull that guides a tossed ball into an elegant arc before it returns to the earth. It is everywhere, always acting, always pulling, and yet of the four forces, gravity is also the weakest, at least when measured in the strength it applies to individual particles. But this is where gravity becomes more interesting than it first appears, because while the strong force dominates at the tiniest scales, gravity is the master of the vast. It is the only force that never cancels out. It has no opposite. Electromagnetic forces with their positive and negative charges can balance one another. Nuclear forces fade quickly and act only across minuscule distances, but gravity is patient. It accumulates, it adds up, and the more mass you gather, the more irresistible its pull becomes. That's why gravity, despite its softness, sculpts the cosmos. It's why planets form from clouds of dust, why stars ignite, why galaxies spin, why black holes collapse. It is the quiet hand that shapes the architecture of the universe. If the strong force is a grip, gravity is a curve, gentle, constant, and inescapable. Albert Einstein reimagined gravity not as a force in the traditional sense, but as a bending of space-time itself. According to his theory of general relativity, massive objects like stars and planets don't pull on other objects directly. Instead, they distort the very fabric of the space around them. Imagine placing a bowling ball in the middle of a stretched rubber sheet. It causes a dip, a well, a curved depression. Now roll a marble across that sheet. The marble doesn't head straight. It curves inward, drawn along the slope. That's gravity. And you, sitting wherever you are gently rolling through one of those invisible wells created by the earth beneath you. This curvature of space-time leads to some effects that are subtle but deeply strange. One of them is gravitational time dilation, the fact that time itself moves more slowly in stronger gravitational fields. If you were to sit near a black hole for a few hours and then return to Earth, you might find that years have passed for everyone else. Not because time felt different to you, but because time itself was different. Gravity doesn't just shape space, it stretches and compresses time. Another beautiful consequence is gravitational lensing. When light from a distant star or galaxy passes near a massive object like a black hole or a galaxy cluster, it bends. Not because the light chooses to curve, but because the space it travels through has been curved. And when that happens, we sometimes see that distant object multiple times, or stretched into glowing arcs, like reflections in a funhouse mirror made of gravity. It's as if the universe has built its own lenses, not out of glass, but out of distortion itself. Despite all this, gravity still carries a strange humility. It does not roar, it does not spark, You cannot shield against it or block it. You can only respond to it by falling. But even the word falling may be misleading. Einstein's insight was that falling is not being pulled, but being free. When you trip and fall, you're not accelerating toward the Earth so much as moving along the natural curve of space-time. Your body briefly forgets resistance and moves as things would naturally move in the absence of any obstruction. This leads to one of the most poetic truths in physics, that an object in free fall is actually experiencing no force at all. Astronauts floating in orbit aren't weightless because gravity is gone. They're weightless because they're constantly falling, but never hitting the ground. Their spaceship curves around the Earth at just the right speed to keep missing it. This is what orbits are, eternal falling guided by curvature. So in this way, gravity is both the gentlest and most majestic of all the forces. It moves with silence. It cannot be shut off. It brings together the farthest distances. It choreographs the movement of stars, planets, moons, and comets in slow, intricate dances that last billions of years. It shapes the horizon of a black hole. It bends time. It does all of this without pushing or pulling, but by telling space how to curve and telling time how to flow. And it's been doing this since the beginning, long before atoms formed, long before stars lit up, long before life learned to wonder. It was gravity that gathered the dust, pulled the gas, ignited the stars, and opened the stage on which the rest of the universe would play out its story. Perhaps that's why we often take it for granted, like a background hum we've always known. But maybe tonight, as you lie back and breathe slowly, you might feel a new appreciation for this soft companion. The force that doesn't shout, doesn't flash, but quietly keeps you grounded, even as the Earth spins beneath you. In the next part of our journey, we'll shift from the steady hand of gravity to the spectacular chaos of exploding stars, from forces that pull to forces that release. But for now, just rest in the thought that the entire universe is quietly curved, and you're already floating along its lines. There's something beautiful about a long, quiet life coming to an end, not because it ends, but because of what it leaves behind. In the universe, that beauty often takes the form of something vast, luminous, and violent. A star, after shining for millions or even billions of years, doesn't always fade softly into the dark. Sometimes it ends in a final brilliant release, a supernova, a death so powerful that it briefly outshines its entire galaxy, a farewell so intense that it becomes a birthplace. Supernovae are among the most spectacular events the cosmos has to offer. But like many grand exits, they happen only under the right conditions. Not all stars go out this way. Most, like our own sun, will one day quietly shed their outer layers and shrink into a white dwarf, a small, dim ember of what they once were. But for larger stars, those at least 8 times the mass of the sun, the ending is more dramatic. Their deaths are written in fire. Let's begin with Type 2 supernova, the kind born from the slow collapse of a giant star. For most of its life, a star balances 2 opposing forces, gravity pulling inward and fusion pushing outward. Deep in its core, hydrogen fuses into helium, releasing energy that holds gravity at bay. As the hydrogen runs out, heavier elements begin to fuse, helium into carbon, carbon into oxygen, and so on, all the way up to iron. And that's where the chain stops. Iron does not release energy when it fuses, it hoards it. So once a star builds up an iron core, the process turns against it. With no more outward pressure to resist gravity, the core collapses. In less than a second, it shrinks catastrophically until the atoms themselves are crushed. Protons and electrons merge into neutrons. The core becomes so dense it essentially becomes a giant atomic nucleus, and then it rebounds. That rebound, like the thud of a trampoline after a fall, sends shockwaves outward. The outer layers of the star are blasted into space at tremendous speeds, heating up, glowing with incredible brightness. For a few weeks, the dying star outshines everything around it, and then it fades, slowly, quietly. What's left behind is often a neutron star, a city-sized remnant of collapsed matter spinning rapidly, with a mass greater than our Sun packed into something the size of a small town. Or, if the original star was even more massive, the collapse might continue beyond even that point, forming a black hole, where gravity becomes so intense that not even light can escape. There's another kind of supernova, just as dramatic but born from a different story. These are the Type Ia supernovae. Explosions not of massive stars but of smaller stars pushed beyond their limits. Picture a white dwarf, the quiet remnant of a sun-like star. Alone, it would remain stable for billions of years, slowly cooling. But in a binary system with a companion star nearby, it may begin to siphon material from its neighbour. Slowly, subtly, it gains mass until it crosses a threshold known as the Chandrasekhar limit. And then, almost without warning, it ignites. The result is a thermonuclear explosion that tears the white dwarf apart. Unlike core collapse supernovae, which leave behind neutron stars or black holes, these Type Ia events leave nothing. The entire star is obliterated, flung into the void as stardust and ash. These explosions are so consistent in brightness that astronomers use them as cosmic yardsticks to measure the expansion of the universe. But the true power of all supernovae isn't just in their brightness, it's in what they give back. During the star's lifetime, it builds heavier elements in its core, but it's only in the explosion, when temperatures soar to billions of degrees, that many of the elements we know can be formed. Gold, silver, iodine, uranium. These aren't made in the hearts of stars, but in their deaths. The calcium in your bones, the iron in your blood, the oxygen in your breath, all were forged in stars that died long before the Earth was born. A supernova is destruction, yes, but it is also a delivery. It seeds the cosmos with raw material for planets, for oceans, for bodies, for thought. And in that way, every person who has ever lived is connected to some long-lost star that once burst apart in silence and flame. We sometimes forget, looking up at the night sky, how much of it is built on ruins. Nebulae glowing in pink and blue are often remnants of ancient supernovae, slowly expanding, their gases illuminated by starlight. The dust that forms new stars and planets is often second-hand, recycled from a star that exploded before. Even Earth carries in its crust the fingerprints of these ancient deaths. There is something strangely comforting in that endings can be beginnings, that a star's collapse can give rise to new light, new chemistry, and eventually, new life. Supernovae remind us that power isn't always about control or preservation. Sometimes the greatest power is in release, in letting go, in becoming part of something larger, something that continues beyond the moment of collapse. As we continue our journey, we'll witness another kind of cosmic outburst. Briefer, brighter, and more mysterious. Gamma-ray bursts, the blink of a dying star seen across the universe. But for now, you might rest in the thought that somewhere out there, a star is giving its final gift to the cosmos, a moment of radiance that, though it may last only days, will echo for billions of years. There are moments in the universe that pass so quickly, they could almost be missed. Blinks, flashes, fleeting sparks in the darkness. But in those briefest instants, energy is unleashed on a scale so vast that it defies the imagination. These are gamma-ray bursts, or GRBS, a name that sounds technical, almost unassuming, until you realise what it actually describes. The brightest, most energetic explosions known to exist in the universe. So powerful, so luminous, that for a few seconds they can outshine everything else in the sky combined. They don't last long, often no more than a couple of seconds, sometimes even less. But in those seconds they release more energy than our sun will produce in its entire 10 billion year lifetime. It's like a firecracker that briefly replaces the moon, a flicker that scorches the memory of space itself. But before we marvel at their intensity, let's gently explore what they are, where they come from, and why they're so important in the story of cosmic extremes. Gamma-ray bursts come in two broad flavours, long G RBS and short G RBS. And though they look similar to our instruments, brief high-energy pulses of gamma radiation, their origins are quite different. Long GRBs are usually the result of a dying, massive star. Much like in a Type II supernova, the core collapses and forms a black hole. But in this case, the star is spinning rapidly, and its magnetic fields are intensely strong. This causes two narrow jets of material to erupt from the poles of the collapsing star, streams of energy and particles travelling close to the speed of light. If Earth happens to lie in the path of one of those jets, our detectors will register it as a burst of gamma rays, lasting anywhere from a couple of seconds to a few minutes. These events are sometimes referred to as collapses, and they are among the most luminous phenomena in the known cosmos. Then there are the short GRBs, events that usually last less than 2 seconds. These are thought to be the result of something even stranger, the collision of two neutron stars, or a neutron star with a black hole. These mergers are unimaginably violent. Picture two ultra-dense corpses of long-dead stars, each the size of a city but with more mass than our Sun, spiralling closer and closer together, warping space-time, releasing gravitational waves, and then finally colliding. In that instant, a tremendous burst of energy is released, not just in gamma rays but in gravitational ripples that travel across the fabric of reality. These short bursts are so fast that if you blink you'll miss them. But what they lack in duration, they make up for in intensity. And for astronomers, they are a source of fascination, because they represent some of the rarest and most extreme events in nature. What's particularly poetic about GRBs is their silence. Despite their power, they occur far beyond the reach of sound. There is no boom, no bang, no ripple through air, just a beam of radiation crossing vast emptiness, arriving silently at our detectors, like a whisper that has travelled for billions of years to finally be heard. In 1997, astronomers detected a gamma-ray burst whose light had been travelling for over 8 billion years before reaching Earth. That means the explosion happened when our solar system didn't even exist yet, when the Earth, the oceans, the trees, and all of human memory were still unimagined. And yet, that moment, brief, invisible, without warning, left a mark that would be picked up by metal and silicon centuries later. A story sent across time, and sometimes these stories come with more than light. In 2017, for the first time, astronomers detected both gravitational waves and a gamma-ray burst from the same neutron-star collision. Two kinds of messengers, one made of light, the other of warping space-time, arriving at Earth within seconds of each other. It was like hearing and seeing a cosmic event in stereo. A new way of listening to the universe was born that day. Though these bursts are rare, they are incredibly important. Some scientists believe that GRBs, if they occur close enough to a planet like Earth, could potentially strip away the atmosphere or damage the biosphere depending on the direction and distance. Thankfully, these events tend to happen in faraway galaxies, and the odds of one being aimed directly at us are incredibly small. Still, their existence is a reminder that the universe is not always gentle. It has quiet storms and silent explosions, events of unspeakable energy hidden in the dark. Yet, even within that violence, there is beauty. The afterglow of a GRB can light up a galaxy. It can help us trace the deaths of massive stars, the births of black holes, and the swirling chaos of colliding remnants. It can even serve as a kind of lighthouse, illuminating the structure of the cosmos between us and the source, allowing scientists to study distant gas clouds and the early universe itself. And so, a gamma-ray burst is not just a blink. It is a blink and a revelation, a moment that seems too short to matter, but which contains within it the power to change everything. A single cosmic flash that echoes across billions of light years. A firefly seen across the ocean of time. As we move forward in our journey, we'll look at yet another kind of stellar death. Stranger than supernovae, longer than GRBS. A star that doesn't just explode once, but continues to echo with power long after its death. These are the hypernovae and the magnetas, stars that break their own bones and scream through magnetic storms. But for now, rest in the stillness after the flash. The sky has blinked, the light has passed, and somewhere, far away, the echo is still unfolding. By now, we've wandered through the luminous deaths of stars, their peaceful fades, their explosive farewells, their sudden bursts that blink across billions of light years. But there are still corners of stellar death that remain stranger, rarer, even more intense. Not louder necessarily, but deeper, like thunder that rumbles in the bones of a galaxy. These are the hypernovae and the agnetas, stars that do not simply go out in a flash, but instead collapse and scream. Not with light, but with force fields so vast and tangled they could tear atoms apart. Let's begin with hypernovae, which you might think of as supernovae taken to their extreme. They occur when the most massive stars in the universe, those many times the size of our Sun, reach the end of their lives. Like their smaller counterparts, these stars burn through their fuel in layers, fusing lighter elements into heavier ones. Eventually, they reach the same grim endpoint. Iron, core of matter too heavy to fuse, too dense to support itself. But in a hypernova, the collapse is even more catastrophic. These stars often spin incredibly fast, and their magnetic fields are monstrously strong. When the core collapses, it doesn't just implode and bounce. It twists, it shears. The energy doesn't release evenly, but is channeled, squeezed, and focused into powerful narrow jets, like a tornado forming inside the heart of a dying star. If those jets punch through the outer layers and escape into space, they become some of the longest-lasting and brightest gamma-ray bursts we've ever seen. Hypernovae are more than just supernovae with volume turned up. They're shaped by angular momentum, magnetism, and the chaos of rapidly spinning cores. They don't happen often, but when they do, they leave their mark, not just in light, but in the surrounding space. The aftermath glows for years, sometimes even centuries. A shell of glowing gas, enriched with newly minted elements, pushed outward by a force that for a moment rivaled the birth of stars. And then, sometimes, what's left behind isn't quiet. Imagine a star collapsing into a neutron star, but not just any neutron star, a magneta. These are among the most extreme objects known to physics. They are neutron stars with magnetic fields so intense that they defy our everyday understanding of what magnetism even is. A typical fridge magnet has a field strength of about 50 Gauss. The Earth's magnetic field? Around 0.5 Gauss. A magnetia, by contrast, can have magnetic fields of a quadrillion Gauss. That's a 1 followed by 15 zeros. A field so strong that, at close range, it could deform the electron clouds around atoms. A magnetic storm that could strip the data from a hard drive from thousands of kilometers away. But magnetars don't just sit there humming quietly with invisible force. Sometimes they quake. The crust of a neutron star is under immense pressure, denser than anything we can reproduce on Earth. Occasionally, the magnetic field shifts, tangles, twists itself tighter, and when it does, it can cause the crust to snap, releasing a sudden, massive burst of energy. This is called a starquake, and the energy it unleashes can be greater than any flare our Sun has ever produced. In 2004, one such burst was detected from a magnetar about 50,000 light-years away. The initial spike of energy was so intense that it briefly saturated detectors on multiple satellites, and the Earth's upper atmosphere changed just from that distant flash. The burst lasted only a fraction of a second, but it released more energy than the Sun emits in 150,000 years. What makes magnetars so captivating isn't just their strength, it's their unpredictability. They sit quietly for years, decades, even longer, and then, without warning, erupt in magnetic storms or short bursts of high-energy light. Sometimes the bursts are small, other times they're cosmic-scale tantrums, and yet, all of this happens within something no larger than a city. A magnetar might only be 20 kilometers wide. That's smaller than some metropolitan suburbs, and yet within that tiny shell is more mass than our Sun, and inside that mass, rotation, magnetism, crusts under tension, fields twisting in silence. If a black hole is a place where gravity has the final word, a magnetar is where magnetism briefly steals the spotlight, coiling and snapping, cracking the star's surface like ice under stress. And while black holes hide everything beyond their horizons, magnetars scream, flaring out across the universe, their light and magnetic ripples echoing through the cosmos like a thunderclap that never quite fades. These are not everyday stars. They are exceptions, monsters born of rare alignments of mass, spin, and field. But their rarity does not lessen their importance. They remind us that power is not always obvious. It doesn't always shine steadily or roar in familiar ways. Sometimes it builds quietly inside a broken shell. Sometimes it releases in less than a second, but changes the space around it for centuries. And perhaps there's something to be learned there too. That strength isn't just about what burns bright. It's also about what resists, what holds together until it can't anymore, what breaks suddenly but leaves behind echoes. A magnetar doesn't ask permission to be powerful. It simply exists, silent and dangerous, until it can no longer remain quiet. As we drift away from these explosions and magnetic storms, we'll leave behind the visible, the measurable, the short-lived spectacles of light. We'll begin to enter the realm of things unseen, of matter that cannot be touched, and energy that repels rather than attracts. We'll meet the invisible architects of the cosmos, the dark matter that binds galaxies together, and the dark energy that pulls them apart. But before we go, rest in the thought that somewhere in the sky, a dead star may be spinning, quiet for now, but not asleep. There's a moment when falling, where it feels like the world gives way, when motion becomes surrender, when the ordinary rules begin to slip one by one into something stranger. And nowhere in the universe is that more true than at the edge of a black hole, a place where even light cannot escape, and time itself begins to bend. The idea of a black hole is older than you might think, long before Einstein's equations, long before the term itself was coined. There were whispers of stars so massive, so dense, that their gravity might trap even light. But it wasn't until the early 20th century, when general relativity revealed gravity not as a force, but as a curvature of space-time, that these whispers became something more, a prediction, a necessity. The equations didn't just allow for black holes, they demanded them. At the center of every black hole lies a mystery, a singularity, a point of infinite density, where matter has been crushed into something beyond our comprehension. Around it is the event horizon, the boundary beyond which no signal, no particle, no hope of return can escape. Not because the black hole pulls harder than anything else, but because the very fabric of space-time inside the horizon has tilted so steeply inward that all paths, even those taken by light itself, lead only further in. To understand this, imagine space-time not as an empty void, but as a stretched fabric. In most places, that fabric is relatively flat. Mass bends it a little, a star curves it gently, a planet dimples it. But a black hole? It doesn't just dimple the sheet. It pulls it into a funnel so deep that the bottom vanishes from view. And near the edge of that funnel, at the event horizon, time begins to act strangely. To an outside observer, an object falling into a black hole appears to slow down. Its descent becomes sluggish. Its clock seems to tick more slowly. Its signals stretch out into redder and redder light until, at the very brink, it freezes. Not because it stops, but because time itself, from the outside's point of view, has nearly come to a halt. The infalling object still experiences time normally, brief, terrifying, unstoppable. But to the outside world, it never quite crosses the line. It becomes a ghost, a memory stretched over space. This time, dilation isn't science fiction. It's been measured in gentler forms, like in GPS satellites, where clocks tick faster than on Earth because gravity is weaker at their altitude. But near a black hole, the effect grows profound. Time slows, lengths contract, directions warp. Space and time are no longer stable backdrops. They are actors, tangled in the drama of mass and momentum. Yet for all their strangeness, black holes are not violent up close. If you were to fall toward a supermassive black hole, say, 1 millions of times the mass of the Sun, you might not feel anything unusual as you crossed the horizon. No sharp tug, no sudden change. The event horizon is not a wall. It is a boundary of no return, not of physical resistance. You'd pass through it the same way you pass through a shadow, quietly, gently, unknowing. Of course, what happens next depends on your size, and the black holes. For small black holes, tidal forces, differences in gravity between your feet and your head, would stretch you into a thin line of atoms, a process affectionately nicknamed spaghettification. But for larger black holes, the journey might feel smooth, for a while, until the centre, where the equations break and no one can say what truly happens. Some think the singularity is a real point, a place where all physics stops. Others believe it's simply a sign that our current theories are incomplete, that we need a quantum theory of gravity, a way to unify Einstein's smooth space-time with the jittery, probabilistic world of particles. Perhaps someday we'll understand. For now, it remains a riddle hidden behind a horizon. But even as we struggle to comprehend their interiors, black holes have become central figures in our understanding of the cosmos. They are not rare. They are not exotic outliers. They are common, even expected. Born from the collapse of massive stars lurking in the hearts of galaxies, quietly shaping the motion of stars and the flow of time. And in recent years, we've begun to see them, not just through inference, but through image. In 2019, the Event Horizon Telescope gave us our first direct glimpse of a black hole silhouette, a glowing ring of light warped around a dark centre, like the eye of a storm. What we saw was not the black hole itself, but the light around it, bent by gravity into a circle of fire. It was a portrait of absence, made visible by the distortion of everything near it. In that image was more than confirmation. There was poetry, a shadow made of gravity, a silence so deep it shapes light, a reminder that power isn't always loud. Sometimes it's the quiet reshaping of reality itself. As we continue, we'll discover that black holes are not just destinations, they are also engines. They feed, they flare, they emit, and in doing so, they light up the universe in ways we never expected. In their hunger, they reveal something else, something that shines. But for now, rest in this paradox. The place where time stops is also where some of the most important stories begin. When you picture a black hole, you might imagine something small, an invisible remnant of a collapsed star lurking in the dark, consuming what strays too close. But deep in the heart of nearly every galaxy, including our own, lies a black hole of a very different kind. It is not small, it is not hidden in the shadows, it is supermassive, containing the weight of millions or even billions of suns curled into a single point, shaping the structure of galaxies not with chaos, but with quiet gravitational authority. These are supermassive black holes, or SMBHs for short, and they are among the most mysterious and influential objects in the cosmos. Unlike the black holes formed from the collapse of stars, these giants are born from a history we don't yet fully understand. Some may have started small and grown slowly by feeding on stars, gas, and even other black holes. Others may have formed rapidly in the early universe, seeded by vast clouds of matter collapsing before stars even ignited. However they began, they've become anchors, gravitational centers not just of attention, but of structure. At the core of our own Milky Way lies one such object, Sagittarius, a star. A supermassive black hole with a mass about 4 million times that of the Sun. It sits quietly now, not devouring stars or shining brightly, but its influence is immense. Stars near it move in fast, tight orbits, circling an object they cannot see but cannot escape. These orbits have been tracked over decades, and they provide some of the clearest evidence that something truly massive and truly invisible resides at the galaxy's centre. But this is not unique to the Milky Way. Observations across the universe reveal that almost every large galaxy harbours a supermassive black hole in its core. And more intriguingly, the size of the black hole seems to correlate with the size of the galaxy's central bulge, suggesting a strange kind of dialogue between a black hole that fits inside a solar system and a galaxy that spans hundreds of thousands of light years. Somehow these two vastly different scales are connected. The black hole does not merely follow the galaxy's growth, it may help guide it. How does something that swallows everything help shape what exists around it? The answer lies in what happens when a supermassive black hole is actively feeding. When gas and dust fall toward the event horizon, they don't always vanish immediately. Instead, they spiral inward, forming an accretion disk, a glowing, spinning ring of material heated to extreme temperatures by friction and gravitational compression. As the material tightens and whirls, it emits immense amounts of radiation, lighting up the region around the black hole with power that can rival the brightness of an entire galaxy. These are active galactic nuclei, and when they are especially bright, we call them quasars, but we'll save that story for the next session. What matters here is that this activity can affect not just the black hole itself, but the entire galaxy. When a black hole feeds, it doesn't quietly sip. It can blow out jets of energy and particles at near-light speeds, sometimes extending for millions of light years. These feedback processes heat and disperse gas throughout the galaxy, regulating star formation and reshaping the surrounding environment. In other words, the black hole at a galaxy's centre might serve as both architect and gardener. It pulls in, but it also pushes out. It shapes not by destroying, but by controlling the flow of matter. If too much gas tries to collapse into new stars, the black hole may heat it, blow it outward, and pause the process. If the galaxy becomes too crowded, the black hole can help create space. This quiet regulation, this balance between feeding and feedback, suggests a kind of partnership between the darkest force in the galaxy and the stars that shine around it. Even more astonishing is the timescale over which this influence plays out. Supermassive black holes grow and change over billions of years. They don't act suddenly. They hum at the rhythm of cosmic epochs. You could live 1,000 lifetimes, and the black hole at the centre of your galaxy would not blink. Its presence is not measured in events, but in gravity's gentle shaping hand. And yet, despite their size and power, supermassive black holes are elusive. You cannot see them directly. Their light, when active, is not theirs, but the result of what surrounds them. Their edges are not physical, but mathematical. They are there, profoundly there, but always behind a veil defined not by substance, but by effect. Perhaps that's what makes them so haunting. They are reminders that influence doesn't always come from brightness or noise. Sometimes the most powerful presence in the room says nothing. It doesn't need to. As we continue, we'll explore what happens when these giants begin to shine, not with their own light, but with the energy of what they consume. We'll meet quasars and blazars, cosmic lighthouses powered by darkness, illuminating the early universe with beams of matter that cross millions of light years. But for now, let your thoughts drift around the quiet gravity at the centre of it all. A presence that doesn't pull you in quickly, but reshapes your path without ever being seen. There's a quiet contradiction at the heart of the universe, something so dark, so thoroughly hidden, it lets nothing escape, and yet under certain conditions, it becomes one of the brightest things we've ever seen. A black hole does not shine on its own. It is by definition a place of silence and absence, and yet, when it feeds, when it draws in matter, it can light up the cosmos. This paradox gives rise to one of the most astonishing objects we've ever discovered, quasars. The word quasar comes from quasi-stellar radio source, a name from an earlier time when astronomers first saw faint points of light in distant galaxies that looked like stars but didn't behave like them. They emitted strange radio signals. Their light was unusually bright and far away. Eventually scientists realized they weren't stars at all, but the fiercely active centers of young galaxies, powered by supermassive black holes devouring matter at an extraordinary rate. Imagine a black hole, millions or billions of times the mass of our sun, surrounded by a swirling disk of gas and dust. As this material spirals inward, friction and gravity heat it to extreme temperatures. The resulting disk glows brightly, not just in visible light, but across the entire electromagnetic spectrum: infrared, ultraviolet, X-rays, even gamma rays. The accretion disk can become so luminous that it overwhelms the rest of the galaxy. From across billions of light years, we see it shining like a cosmic lighthouse. Quasars are some of the oldest, most distant, and most energetic objects we've ever observed. Their light has travelled for billions of years to reach us, meaning we see them not as they are now, but as they were when the universe was young. They're not just fascinating, they're time machines. By studying them, we peer into the early days of galaxies, witnessing how the universe evolved from its fiery beginnings into the rich tapestry of stars, gas, and planets we see today. But sometimes, these luminous hearts of galaxies do more than just glow. They erupt. As the black hole devours matter, some of the material doesn't fall inward but is instead flung outward along its rotational axis. These are relativistic jets, narrow beams of charged particles moving at nearly the speed of light. These jets can stretch across entire galaxies, extending millions of light years into intergalactic space. They are among the most powerful structures in existence, fueled by processes we still don't fully understand, perhaps involving magnetic fields twisted by rotation, flinging matter outward with unimaginable force. When one of these jets happens to point almost directly at Earth, we give the object a different name, a blazar. To our instruments, blazars appear to flicker and blaze, emitting bursts of light and radiation across multiple wavelengths. Because we're looking directly down the barrel of the jet, the radiation appears amplified, like a flashlight pointed straight into your eyes. They are not inherently more powerful than quasars, they're just aligned with our view in such a way that their emissions become dazzling. This orientation effect reminds us how deeply the universe depends on perspective. Two objects might be identical in structure and behaviour, but one looks ordinary, the other blinding, depending only on the angle at which we observe it. Blazars, in a sense, are quasars in performance mode. The same engines, seen from a different seat in the cosmic theatre. There's a kind of poetry in this, that the darkest things in the universe, black holes, can create some of its brightest lights, that falling into silence can become a scream, That matter being lost can generate beams that travel further than light from any star. The jet of a quasar is not an escape from the black hole, but a side effect of its hunger. Light from the abyss, born not in defiance, but in orbit. These cosmic beams are more than just beautiful. They carry clues about how galaxies form and evolve. They influence star formation, heat intergalactic gas, and may even regulate the growth of the galaxies that host them. Like a heart that pumps not just blood but rhythm, black holes at the centre of galaxies shape the structure and future of everything that orbits them. Sometimes we catch these jets bending, curving through space as they interact with interstellar clouds, or lurching as if jolted by invisible tides. Sometimes they flicker and surge with no obvious cause, reminding us how much we still don't understand. Magnetic fields, particle acceleration, quantum effects near the event horizon, it's all part of the machinery, but the details are still being unravelled. Still, what we do know is this. These luminous emissions from active galactic nuclei, quasars, blazars, Seyfert galaxies and more, are beacons not just of power, but of ancient history. They are fossils made of light, messages from a universe that was younger, more turbulent, more ambitious. And despite their distance, they reach us with astonishing clarity. The photons we collect from a quasar may have started their journey billions of years ago, travelling in straight lines across expanding space, slipping between galaxies, skimming past stars, finally reaching a telescope on Earth, a mirror, a sensor, a mind. And in that moment, we do something extraordinary. We see a black hole shine. As we near the end of our exploration of black holes, one more story remains. One that pulls us not outward, but backward, into the possible past. A kind of black hole not formed from stars or galaxies, but from the very birth of the universe itself. Next, we'll explore primordial black holes, ancient invisible relics that may still be hiding in the shadows, carrying secrets not just of gravity, but of everything that came before. But for now, let the light of quasars linger in your thoughts, a blaze born from darkness, a jet born from falling, a reminder that even at the edge of the void, something still shines. There's something quietly haunting about the idea that not all black holes are born from dying stars. Some perhaps were born before stars even existed, before the first light, before atoms, before time flowed as it does now. These are the primordial black holes, and though we've never seen one directly, they might be among the oldest entities in the universe, older than galaxies, older than gravity itself in the form we know it. Tiny echoes from the very beginning. To understand primordial black holes, we must travel back to the first fraction of a second after the Big Bang. A moment when the universe was smaller than a grain of sand, hotter than a billion suns and filled with ripples, tiny variations in density and energy, seeded perhaps by quantum fluctuations. Most of these ripples would go on to form galaxies, stars, and everything else we now see. But some might have been dense enough even for a fleeting instant to collapse into black holes. No stars involved, no fusion, just space, squeezed too tightly, curling in on itself. These would not be the giants we've met before. Some might be the size of mountains with the mass of Earth. Others might be as small as a grain of sand, but heavier than a city. Some could be even smaller still, invisible to any telescope, lurking in the dark like pinpricks in the cosmic fabric. If they exist, they might still be here, drifting through galaxies, orbiting stars, perhaps even passing silently through our own solar system. But what makes primordial black holes so intriguing isn't just their possible age or size, it's what they could be. Some theories suggest they might explain dark matter, that mysterious invisible mass that holds galaxies together, outweighing normal matter by a factor of 5, yet never glowing, never scattering light. We don't know what dark matter is. we've ruled out many possibilities, but primordial black holes, massive enough to affect gravity, small enough to avoid detection, remain on the table. It's an elegant idea that the missing mass of the universe might not be some exotic particle, but a population of ancient black holes scattered like forgotten seeds, born before memory, carrying no light, yet shaping the galaxies from the shadows. But there are problems. If there were too many small black holes, we'd see their effects: gravitational lensing, disruptions in stars, collisions detectable through gravitational waves, and yet we haven't. Not enough to confirm, not enough to deny. They remain a maybe, a possibility tucked between the known and the imagined. Some physicists have gone further still, suggesting that primordial black holes might not just exist, they might carry information about other universes. In certain models of the multiverse, black holes can act as bridges, wormholes, or even seeds of new realities. When a region of space becomes dense enough, instead of collapsing into a singularity, it might bounce, birthing a new expanding universe on the other side of the event horizon. A cosmic sprout, invisible from our side, but blossoming elsewhere. We cannot test this, not yet, but the mathematics allows it. And sometimes the mind needs places like this, places where possibility outruns certainty, and where the universe opens not into a wall, but into a horizon we cannot yet cross. Then there's the idea of Hawking radiation, proposed by Stephen Hawking in the 1970s. He showed that black holes, contrary to popular belief, aren't entirely black. Quantum effects near the event horizon should allow them to slowly emit radiation, losing mass in the process. Over vast timescales, black holes could evaporate. Large ones would take longer than the current age of the universe, but tiny primordial ones, they might be vanishing now, popping out of existence in flashes of high-energy light somewhere in the vast darkness. We've never detected Hawking radiation, but the theory is elegant, and it connects gravity, quantum mechanics, and thermodynamics in a way that has reshaped modern physics. If tiny black holes are vanishing, their final flashes could help us understand the earliest conditions of the cosmos, and maybe, just maybe, point the way toward a deeper theory of everything. It's strange, isn't it, that something so small, so ancient, so hypothetical might hold the answers to so many of our questions, that we might be surrounded by ancient holes in space, each one a silent story from the universe's first breath. And yet, whether they exist or not, primordial black holes invite us to think differently, to step outside the visible, to imagine the unseen and give it weight. They remind us that the cosmos is not only vast in space, but in time, and that the oldest things are often the most silent. As we leave behind the shadows of black holes, those formed in stars and galaxies, or perhaps in the Big Bang itself, we turn now towards something even stranger. Forces not born of mass but of motion, energies that stretch across the universe not as particles but as pressure, not as substance but as emptiness. In the next part of our journey we'll meet dark energy, the quiet expansion of the void, and dark matter, the invisible skeleton of the universe. But for now, pause here, in the silence between galaxies, in the maybe, in the thought that something might be drifting through space, smaller than a grain of sand, older than time, and heavier than anything you've ever held. Something you can't see, but something that sees you, in the way your galaxy moves, the way stars orbit, the way the universe holds together despite everything we don't yet know. When you look out at the night sky, at stars shimmering from across the vastness of space, at galaxies swirling like silent whirlpools of light, you might be tempted to think you're seeing the universe in full. After all, light travels so far, reveals so much. But what if most of what exists never shines? What if the very framework of the cosmos is made of something not only unseen but unseeable, at least by ordinary means? This is the mystery of dark matter, and it's not a small one. In fact, it may be the largest unresolved presence in the universe. Scientists believe that roughly 85% of all matter is dark, not because they've seen it, but because they've seen what it does. The first clues came not from advanced space probes or particle colliders, but from a quiet revolution in how we understood galaxies. In the 1970s, astronomer Vera Rubin began measuring how stars moved around the centres of spiral galaxies. According to Newton's laws, and common sense, you'd expect stars near the edges of galaxies to orbit more slowly than those near the centre, just as the outer planets in our solar system take longer to orbit the Sun than Mercury or Venus. But Rubin found something strange. The stars far from the galactic centre were moving just as fast as those closer in. It was as if an invisible hand was holding the galaxy together, adding unseen mass to keep everything from flying apart. That invisible hand has come to be known as dark matter. It doesn't emit or reflect light. It doesn't interact with the electromagnetic force in any detectable way. Yet its gravitational pull is unmistakable. It shapes galaxies, forms vast cosmic webs, and bends the light from faraway sources through a phenomenon called gravitational lensing, curving light around itself like a glass marble might bend a beam of sunshine. We see its fingerprints in the patterns of how galaxies cluster. We detect its pull in the way light from background galaxies warps when it passes through unseen mass. We simulate its presence in computers, and only then do we recreate the vast cosmic structures we observe in space, the filaments and clusters, the delicate balance of star formation and collapse. Without dark matter, our models fall. Apartment galaxies spin wrong. Structure doesn't form. The universe begins to look oddly empty. And yet, no one has ever seen a dark matter particle. What could it be? Many theories have been proposed, each more fascinating than the last. One leading idea is that dark matter consists of WIMPs, weakly interacting massive particles. These hypothetical particles would have mass, and therefore gravity, but would barely interact with normal matter at all, streaming through planets, stars, and even people without leaving a mark. If this theory is correct, then trillions of dark matter particles may be passing through your body each second, completely unnoticed. Their interactions are so rare, so quiet, that detecting even one is like trying to hear a single raindrop in a storm with earmuffs on. To find them, physicists have built elaborate detectors deep underground, in mines and mountains, shielded from cosmic rays and background noise. They wait for the rarest of events, a single dark matter particle bumping into a regular atom. So far, these detectors have found nothing conclusive. Some tantalizing signals, yes, but nothing that confirms or denies the theory. Other candidates include axions, incredibly light particles predicted by some extensions of quantum theory, and even sterile neutrinos, hypothetical cousins of the ghostly neutrinos we know, but that interact only through gravity. More speculative ideas involve entire classes of hidden particles, or mirror worlds, or particles that change their nature depending on where they are in the universe. And then there are the more exotic possibilities, like primordial black holes, ancient compact objects formed in the earliest moments after the Big Bang, which may behave like dark matter if they are small, numerous, and scattered across the cosmos. No single theory has triumphed. For now, the mystery remains intact. But even without knowing what dark matter is, we know what it does. It binds, it holds, it steadies the dance of galaxies. It reaches across millions of light years, pulling together filaments of matter that cradle the luminous islands we call galaxies. Without it, the stars would drift apart. Planets might never have formed. Even life, balanced delicately on the edge of gravity, might not exist. And dark matter might not be entirely passive. Some theories suggest that under certain conditions, dark matter particles could annihilate one another, converting their mass into energy in sudden bursts. Telescopes have searched for these rare flashes, particularly in regions of the universe where dark matter might be densest, like the centres of galaxies or ancient cosmic halos. Whether these flashes exist remains unclear, but if confirmed, they would offer not just proof of dark matter's identity, but a new kind of window into how the cosmos changes over time. For now, dark matter remains an enigma, felt but not seen, modelled but not measured, everywhere and nowhere. It's a reminder that not all power is visible. Some of it works behind the scenes, quietly, persistently, like a hidden frame beneath a great canvas, invisible to the eye, but essential to everything painted above it. As we drift from the gravity of what holds us together, we'll now move toward the force that pushes everything apart. Not a pull, but a pressure. Not a presence, but a restlessness. In the next session, we'll meet dark energy, the strange, invisible breath of the cosmos, stretching it wider and wider with every passing second. But tonight, let the stars spin in your imagination, not as lonely lights, but as dancers guided by unseen hands, held gently in place by something ancient, something silent, something that may never speak, but is always, always there. If dark matter is the silent hand that holds galaxies together, dark energy is the quiet breath that pushes them apart. It is not a force you feel, or a particle you can catch. It doesn't light up the sky or ripple space like a passing wave. And yet, it might be the most powerful influence in the cosmos, not because of its strength in a single moment, but because it never stops. It keeps going. It expands space itself, gently, relentlessly, with no centre, no edge, and no apparent reason to stop. To understand dark energy, we must begin with a discovery that surprised almost everyone. In the early 20th century, astronomer Edwin Hubble showed that the universe was expanding. Galaxies were moving away from each other, their light stretched toward the red end of the spectrum, like the fading echo of a receding song. This wasn't entirely unexpected. Einstein's equations had hinted at a dynamic universe, though he initially resisted the idea. What Hubble did was provide the observational proof. Space itself was growing. For decades, scientists believed this expansion was slowing down. After all, gravity pulls things together. Even if the universe had started with a great burst, the Big Bang, its growth should gradually decelerate as the matter within it tugged inward. Like a ball thrown into the air, rising but eventually slowing under gravity's pull. But then, in the late 1990s, two independent teams of astronomers studying distant Type Ia supernovae, those bright, consistent explosions in faraway galaxies, found something unexpected. The light from these exploding stars wasn't just redshifted, it was more redshifted than predicted. The galaxies weren't just moving away, they were accelerating. The universe, rather than slowing down, was speeding up. This was a profound shift. Something, it seemed, was pushing space to expand faster and faster, not just resisting gravity, but overwhelming it. That something became known as dark energy. We don't know what it is. We don't know where it comes from, but we know it accounts for nearly 70% of the total energy content of the universe. More than dark matter, more than stars, gas, or dust. It is the dominant presence, quietly expanding space at every point, like invisible taffy being stretched. One way to understand it is to imagine that empty space itself has energy, that even in a vacuum, where there are no particles, no fields, no light, there is still something, a kind of baseline hum, a pressure with no direction, not like wind or waves, but like the expansion of a balloon. As space grows, there's more space for dark energy to act, and so the process accelerates. It's not that galaxies are being pushed through space, it's that space itself is stretching, carrying galaxies with it like dots on the surface of an inflating sphere. And this stretching has consequences. If dark energy continues as it is now, the universe will keep expanding forever. Over unimaginable timescales, galaxies will drift apart, no longer bound even by gravity. Stars will burn out, black holes will evaporate. Eventually the universe will fade into heat death, a quiet, cold emptiness where energy is so thinly spread that nothing more can happen. No reactions, no change, just silence. But some theories suggest a more dramatic ending, the Big Rip. In this scenario, dark energy doesn't stay constant, it grows stronger. Over time, its repulsive force overwhelms all other forces. First, it pulls apart galaxies, then solar systems, then planets, then atoms. In the final moments, even the fabric of space-time is torn apart. The universe ends not in a fade, but in a shattering. This is speculative. We don't know whether dark energy is constant or evolving, but even in its quietest form, it changes the fate of everything. Curiously, the idea of a repulsive force in the universe isn't new. Einstein himself included a term in his equations called the cosmological constant, which added a kind of anti-gravity, designed, ironically, to keep the universe from expanding or collapsing. When Hubble discovered the expansion, Einstein called the constant his greatest blunder, but now it appears he may have been right after all. That constant may very well represent dark energy, or at least behave like it. Some theories connect dark energy to the quantum fluctuations of empty space, which we'll explore more deeply in the next session. Others tie it to new fields or particles that permeate the universe. Still others suggest that our understanding of gravity itself might be incomplete, that the equations bend differently at cosmic scales. For now, we don't know, but the effects are real, measurable. The expansion is happening, the acceleration is continuing, and the universe is becoming larger, colder, and quieter with every passing second. There's something deeply peaceful and a little eerie about this. A universe that isn't ending in fire or collision or collapse, but in stillness, in distance, in quiet. Not with a bang, but with a stretch. Perhaps the most poetic part of dark energy is how it reveals that emptiness is never truly empty. That even in the silence between galaxies there is motion. That space is not a blank canvas, but a participant. Not just the stage, but part of the performance. And so, as we move forward, we'll take a closer look at that stage, at the vacuum itself, at the strange idea that even nothing is full of something, a low hum, a constant murmur, a field that never rests. But before we go, take a moment to imagine this. The space between you and the stars is growing, not quickly, but steadily. And tomorrow it will be a little larger, and the day after larger still, and that this expansion, slow and invisible, is the very breath of the universe, a breath that never ends. When we hear the word vacuum, we tend to imagine silence, emptiness, a place where nothing stirs and nothing lingers. It evokes the idea of pure stillness, a space entirely absent of substance, where no particles float and no waves ripple. But in the strange realm of quantum physics, this idea of nothing begins to blur, because even the emptier space, when examined closely enough, turns out to be teeming with activity. The vacuum, it seems, is never truly empty. It hums, it twitches, it breathes, and from that quiet, restless buzz may come some of the most profound forces in the universe. This hidden movement is known as vacuum energy, and it emerges from the peculiar rules of quantum field theory. At the smallest scales, everything is a field, not just electricity or magnetism, but all particles and forces. Electrons, quarks, photons. They're not little marbles, but ripples on invisible fields that extend across all of space. Even in regions where no particles are present, these fields still exist, and according to quantum mechanics, they can never be completely still. This is the idea of zero-point energy, the lowest possible energy state of a quantum system. You might expect that zero energy would mean absolute calm, but in quantum theory, uncertainty rules. You can't simultaneously know the exact position and momentum of a particle. That same uncertainty applies to fields. Their energy fluctuates even in their lowest state. The result? Space is filled with tiny, fleeting bursts of activity. Particles and antiparticles briefly appear, interact, and disappear again. They're called virtual particles, not directly observable, but indirectly real. One of the most striking demonstrations of this comes from a curious experiment known as the Casimir effect. If you place two very thin, parallel metal plates close together in a vacuum, just a few nanometers apart, they will experience a gentle force pulling them toward each other. Not because of gravity, not because of heat or pressure, but because the vacuum between them is slightly quieter than the vacuum outside. The allowed wavelengths of virtual particles between the plates are limited, while outside the plates, they buzz freely. The imbalance creates a buzzer's tiny push, a whisper of force born from emptiness itself. It's subtle, but it's real, and it shows us that space, even when stripped of every atom and photon, still contains energy, still stirs. This vacuum energy may be connected to the dark energy we spoke of earlier. After all, if empty space has a kind of built-in pressure, a natural tendency to stretch, it might explain why the universe's expansion is accelerating. In this view, dark energy is not something added to space, but something that was always there, embedded in the nature of the vacuum itself, a quiet engine that powers the cosmos forward, second by second. But here's where things get complicated. When physicists try to calculate the energy of the vacuum using quantum field theory, the result is enormous. Not just large, not just massive, but staggeringly, absurdly high. Off by a factor of 10 to the 120th power compared to what we actually observe. That's a number so large it has no natural comparison. If you wrote it out fully, the page would drown in zeros. This mismatch is known as the cosmological constant problem, and it is one of the great unsolved puzzles in physics. Why is the vacuum energy so small in practice, when theory suggests it should be so large? Why doesn't space tear itself apart instantly? What balancing force, or hidden mechanism, tames the restless vacuum into something so gentle that we barely notice it? Some suggest that only in universes with the right amount of vacuum energy can galaxies form and stars shine and life arise. That we live in this universe not because it's the only one, but because it's one of the few where observers like us can exist. This is part of the anthropic principle, which we'll explore later. For now, it's enough to sit with the question, why does emptiness behave so precisely? There's something profoundly calming in the thought that the vacuum isn't silent, that beneath the quiet of space there is a soft, invisible activity, a dance too fast, too small for us to perceive. It reminds us that even when nothing seems to happen, something is always at work. That motion continues in stillness, that even the dark has texture, and yet despite this restless activity, the vacuum is the stage on which all the drama of the cosmos plays out. Stars are born in it, galaxies drift through it, light travels across it for billions of years. Even the most powerful explosions, supernovae, quasars, gamma-ray bursts, are carried on its back. It is, in a way, the quietest and most patient thing in existence. Perhaps that's what makes it so powerful. Not its noise, but its steadiness. Not its presence, but its backgroundness. Like a whisper that never ends. Like a hum that carries everything, but demands nothing. As we move forward, we'll leave the vacuum behind, and yet, we'll carry it with us. Because in our next session, we'll explore the most speculative and delicate structures the early universe might have, left behind cosmic strings, infinitely thin, fantastically dense, and possibly still trembling through space even now. They may never have existed, or they may be cutting across the universe right this moment, unnoticed. And either way, they're a reminder that power is not always about explosion or expansion. Sometimes it is about the shape of things, the hidden lines, the threads, but for now, rest in the emptiness, or rather, in the idea that emptiness is never truly empty. That space beneath everything has a pulse, and that the quietest forces may be the ones that hold the universe most gently. We've journeyed through forces you can feel, like gravity's quiet pull, and through ones you cannot, like dark energy's invisible stretch. We've passed collapsing stars and glimmering jets, the buzz of quantum nothingness, and the silent sway of unseen matter. But now, we arrive at a place stranger still, a realm where science meets possibility, and the universe might be threaded with lines that no eye has ever seen, and no hand has ever touched. These are cosmic strings, and though they remain entirely theoretical, they offer one of the most elegant visions of hidden power we've ever imagined. Cosmic strings are not strings in the ordinary sense. They are not threads or cords floating in space, swaying like hair in the wind. Instead, they are one-dimensional defects, infinitesimally thin but immensely dense lines that may have formed in the earliest moments after the Big Bang. Think of them not as objects within space, but as faults in the fabric of space itself, like cracks in ice that froze too quickly, like creases in a sheet of paper that tried to flatten itself too fast. To understand where these strings might come from, we need to think about phase transitions. In physics, when a system cools, it can change its structure. Water freezes into ice. Iron becomes magnetized. The early universe may have undergone similar transitions, shifting from one kind of energy state to another as it cooled. During these shifts, the laws of physics themselves may have changed slightly, and in the process, imperfections might have been left behind. Cosmic strings could be such imperfections. Not things that were added to the universe, but things it couldn't quite smooth out. And while they would be impossibly narrow, thinner than a proton, the amount of energy packed into one of these lines would be vast. A single cosmic string stretching a kilometre could weigh more than Mount Everest. If it were a loop, its gravitational pull might bend space around it so sharply that it could lens light like a magnifying glass, or even allow a shortcut through space-time. Some theories go further still. In certain models of string theory or high-energy physics, cosmic strings might move at nearly the speed of light. They might form loops, vibrating and radiating gravitational waves. If two strings crossed and interlinked, they could snap, releasing bursts of energy that ripple across the universe. These bursts might be detectable, not with our eyes, but with instruments that can sense the trembling of space itself. And though we've never seen a cosmic string, scientists have looked. We've scanned the sky for lensing patterns too sharp to be caused by ordinary matter. We've listened for unusual gravitational wave signatures, odd echoes in the deep hum of the cosmos. So far, nothing conclusive has appeared, but that doesn't mean they're not out there. If cosmic strings exist, they might be rare, or quiet, or scattered across expanses so distant that we've simply not noticed them yet. Still, they remain an intriguing possibility, not just as relics of the early universe, but as keys to deeper laws. If we could detect one, even indirectly, it might tell us about physics beyond the standard model, about grand unified theories that weave together the forces of nature into a single framework, about what happened not 1 billion years ago, but 1/trillionth of a second after everything began. There's also a poetic symmetry in the idea that the universe might be stitched together with lines of unimaginable energy. That beneath all the galaxies and stars and swirling gas, there might be threads, not metaphorical ones, but real, physical features marking the seams of cosmic birth. The very idea invites reflection. If space can hold on to such scars for billions of years, what other echoes from the beginning might still surround us? And yet, for all their grandeur, cosmic strings would be silent. You would not see them as you passed by. You would not feel their pull unless you were very, very close. You might live an entire life within a universe crisscrossed by them and never know they were there. Their power is not in light, or sound, or heat. It is in structure, in the potential they carry, in the equations they satisfy, waiting patiently for us to notice. In many ways, they are the perfect way to close this part of our journey, because cosmic strings are influence without attention. Like dark matter, they shape without shining. Like vacuum energy, they hum without moving. And like gravity, they connect things not by force, but by presence. As we look forward to the next part of this exploration into the origins of the universe and its possible fates, cosmic strings leave us with a quiet question. If the universe has memory, might these be its wrinkles? If the early moments of existence were turbulent and wild, could these be its fossilized echoes? Or perhaps they are simply ideas, beautiful ones, elegant speculative whispers of a physics not yet written down. Either way, let the thought linger, that somewhere out there space itself may be folded, that between the stars in the silence there might be lines drawn not by hands, but by the universe remembering how it once became itself. Before stars lit the sky, before atoms found each, other in the dark, before space had depth or time had rhythm, there was something we call the Big Bang. Not a bang in the traditional sense, not a sound in space, not an explosion in air. It was everything. Energy, matter, time, and space. Beginning, not from somewhere, but from everywhere at once. The phrase Big Bang can be misleading, evoking images of a fireball erupting into an empty void. But there was no void to begin with. There was no outside into which the universe expanded. The Big Bang was the moment when space itself began to stretch, when time began to flow, and when the physical laws that shape everything, from falling apples to fading starlight, first settled into being. It was not an event inside the universe. It was the birth of the universe itself. And with that birth came power. Power not in the explosive sense of thunder or flame, but in the profound, almost unfathomable sense of transformation. Every ounce of structure, every breath of energy, every galaxy that ever spun into existence was compressed into a singular state, a tiny, hot, dense condition beyond comparison. Some call it a singularity, though our equations falter there. They loop into infinities, they stop making sense. And in that sense, the Big Bang wasn't just a beginning. It was a boundary, a veil. For the first minuscule fraction of a second, less than a trillionth of a trillionth of a trillionth, the universe may have undergone an extraordinary period of expansion known as cosmic inflation. In this fleeting instant, space itself ballooned faster than the speed of light, not violating any laws, but stretching the very fabric that those laws would come to govern. Distances that were once microscopic became galactic. Tiny fluctuations in the quantum foam, barely perceptible ripples, were stretched into patterns that seeded the arrangement of all future galaxies. These ripples weren't just noise, they were the first structure. As inflation slowed, the energy it carried didn't vanish. It transformed into particles, into forces, into light and matter. This is the earliest act of cosmic alchemy, energy condensing into mass, as described by Einstein's famous equation E equals mc squared. Out of this first breath of becoming, the universe cooled enough for quarks to emerge, combining into protons and neutrons. Within minutes, those protons and neutrons fused into the first atomic nuclei, mostly hydrogen and helium, along with traces of lithium, and then the universe entered a waiting period. It would take hundreds of thousands of years for the temperature to fall enough for electrons to slow down and settle into orbit around those nuclei, forming the first stable atoms. And when they did, the universe shifted from opaque to transparent. Photons, light particles, were finally free to travel unhindered, creating a soft afterglow that still fills all of space. This light, now stretched into microwaves by billions of years of expansion, is the cosmic microwave background, a faint but persistent whisper of that first shining release. And yet, for all its profound significance, the Big Bang is not something we can see directly. We can observe its echo, we can simulate its early moments, we can study the results of its first billion years, but we cannot peek through the curtain of that beginning. Our equations stop short, our tools fall silent. In that sense, the Big Bang is not a knowable point. It is a limit, a cosmic horizon. Still, we try. Some theories suggest that before the Big Bang, if before is even the right word, there may have been other universes or other cycles. That the Big Bang was not a singular event, but one in a series, a bounce, a rebirth. Others suggest that what we see as a singularity is the smooth interface of higher dimensional space, what string theory calls a brane collision, like two cosmic sheets gently colliding in a deeper reality. These are not answers, but they are directions, threads to follow. What is clear is that the Big Bang unified the forces of nature into a single, blisteringly hot, elegant whole. At the earliest times, the strong nuclear force, weak nuclear force, electromagnetism and gravity may have been indistinguishable, blended into a single interaction that we no longer see directly, but whose fingerprints remain imprinted in the shape and evolution of the cosmos. As the universe cooled, these forces began to separate like steam condensing into rain, each revealing its own distinct role. This unfolding, this differentiation, is what gave us the complexity of atoms, chemistry, stars, and life. So when we ask what was the most powerful moment in the universe, the answer may be simple: this one. Not because it burned brighter, or roared louder, or shattered something vast, but because everything came from it. Every moment of warmth, every fall of a leaf, every heartbeat, every solar flare, every spiral arm of every galaxy, none of them could have existed without that beginning. Not as an explosion, but as a birth, a transition, a quiet but unstoppable unfolding. It is tempting to think of the Big Bang as distant, something that happened long ago in some unreachable past. But it is not entirely separate from us. You're not watching its aftermath. You are its aftermath. The atoms in your hands, the breath in your lungs, the thoughts forming even now as you listen. These are not exceptions to the Big Bang. They are its echo. They are its continuation. So tonight, as you rest beneath a sky still expanding, let your mind drift backward, not to an origin of time, but to the first time time could begin, to a moment that contains all other moments, a moment not of sound or fury, but of becoming, of emergence, of the soft unfolding of everything. We tend to imagine the end of the universe in fire, in ice, in slow drifting silence. We picture galaxies fading one by one, stars blinking out like candles in a cold wind. But there's another ending that scientists whisper about, not with panic, but with quiet fascination. It's not loud, it's not slow, it doesn't give warning, and in the most unsettling twist of all, it begins not with something breaking, but with something slipping. This is the idea of vacuum decay, a catastrophe not of collision or collapse, but of rearrangement, a change not in matter, but in the very foundation beneath matter. It's a concept that sounds like science fiction, but is rooted in the strange, mathematically consistent world of quantum field theory. And though it might be the most extreme expression of cosmic power we can imagine, it doesn't shout, it whispers, it hums beneath everything, and if it ever begins, we'll never see it coming. Let's begin with the vacuum. That is, what we think of as empty space. Earlier we explored how the vacuum is not truly empty. It's filled with fields, with jittery fluctuations, with potential. In quantum physics, vacuum refers to the lowest energy state a field can occupy. But what if the vacuum we live in, the one that allows electrons to orbit atoms, light to move at its familiar speed, and stars to shine as they do, isn't the lowest possible state? What if it's only a local minimum, like a ball resting in a shallow dip on a hillside, unaware that a deeper valley lies just beyond? This is the idea of a false vacuum. Our universe may exist in a metastable condition, stable enough to last for billions of years, but not the absolute bottom of the energy landscape. And just as a ball can, through a jostle, find its way out of a shallow well and tumble down into a deeper one, so too might our vacuum undergo a shift, a quantum tunneling event, triggering a phase transition across all of space. What would that mean? It means the very constants of nature, those delicate numbers that determine the strength of gravity, the charge of an electron, the masses of fundamental particles, could suddenly change, and not gradually, instantly. A bubble of true vacuum would appear somewhere in the universe, and from that point, it would expand outward at the speed of light. Inside this bubble, physics would be rewritten. Chemistry would no longer behave the way it does. The structures that form matter might not hold together. Atoms might dissolve. The very definition of existence could shift into something unrecognizable. Because the bubble expands at light speed, no signal could warn us. There would be no glow in the sky, no earthquake or gravitational shiver. Just the ordinary world, then not. But this isn't the stuff of horror. It's not a prediction. It's a possibility, drawn from equations that describe how energy fields behave. One key clue comes from the Higgs field, the field responsible for giving particles their mass. In 2012, the Large Hadron Collider confirmed the existence of the Higgs boson, and with that, allowed physicists to estimate the shape of the Higgs field's potential energy. The results suggest we might live in a metastable vacuum, not doomed, but not at the deepest valley either. Yet even if this is true, vacuum decay is an extremely rare process. The conditions required to trigger it naturally are so extreme that they likely haven't occurred since the universe was very young. The lifespan of a metastable vacuum can be longer than the age of the universe itself, perhaps unimaginably longer. And so, despite its elegance and drama, this is not something we expect, only something we acknowledge. But there's something poetic in it too, because if vacuum decay ever occurs, it won't be because something failed. It won't be a war or a weapon or a firestorm. It will be the universe quietly remembering that it can be different, that the laws we take as permanent, unchanging, absolute, are perhaps just temporary arrangements, stable for now, but subject to change if the fields that define them decide to shift. And that realization changes how we think about power. We've spent much of our journey looking at forces, at strength, gravity, pressure, fusion, rotation. But here is a form of power that doesn't need motion, that doesn't need energy to be released. It is potential, resting everywhere, waiting patiently. It is the idea that the structure of reality is not fixed, but conditional. That what we call everything is just a version, one story among many, and perhaps, instead of fear, that idea can invite humility, that the universe is not finished, that it is still choosing how to be, that behind the scenes of galaxies and stardust and swirling time there may be other possibilities, waiting in silence, not better, not worse, just different. So tonight, as you close your eyes, don't think of vacuum decay as an ending. Think of it as a reminder that what is stable is also fragile, that what feels permanent is also precious, that everything we love, Every moment of curiosity, of joy, of kindness takes place within a vacuum that chose for now to let such things exist, and that the quietest powers are sometimes the most profound. Somewhere between the collapse of stars and the cooling of clouds, between the quiet humming of atomic bonds and the rustle of leaves under your feet, something extraordinary happened. Out of matter forged in heat and silence, out of atoms scattered by explosions older than memory, you emerged, not just as a body of cells and systems, but as a being who can wonder, who can look up at the stars and ask where you came from and why you care. This may be the strangest expression of power in the entire universe. Not gamma rays or black holes, not gravity or dark energy, but something smaller, softer, and infinitely more personal. Consciousness. The ability of the universe to know itself, even if only briefly, even if only through the thoughts of creatures like you. It all begins, as so many cosmic stories do, with stars. In the core of a massive star, hydrogen fuses into helium. That process continues layer by layer until iron is formed, the final stage of fusion that gives no more energy back. Once iron takes over, the star can no longer support itself. Its life ends not with a whimper, but with a supernova, a cataclysm that tears it apart in a blaze of energy and motion. And in that death, something astonishing happens. Heavier elements are born: gold, calcium, carbon, oxygen. All the building blocks of planets, oceans, lungs, trees and brains. These elements don't form in quiet places. They are the ashes of violence, the dust of old catastrophes, and every atom in your body, every breath you've ever taken, every beat of your heart is built from that. The iron in your blood, formed in the last seconds of a dying star. The calcium in your bones, cooked in a stellar furnace. The oxygen you breathe, the carbon in your muscles, the phosphorus in your thoughts. All of it, once drifting in interstellar gas long before the Earth even had a name. This isn't poetry, it's chemistry, it's physics. And yet, it feels like both. You're made of recycled stardust, yes, but you're also more than that. You're not just the material, you're what that material is doing. Atoms do not think, molecules do not dream, proteins do not imagine the sky, but arrange them in just the right way and something new appears, not in substance, but in pattern, in the organisation of neurons, in the exchange of electrical signals, in the endless flickering between what was and what might be. Out of a nervous system emerges awareness, memory, emotion, thought. And that emergence is not trivial, it's not incidental, it is one of the rarest, most complex phenomena we know. In a universe governed by impersonal laws, gravity pulling, entropy rising, life is a rebellion. It collects order, it builds structure, it uses energy not just to burn but to become. And among the countless forms that life has taken on this small planet, one of them gained the capacity to wonder where it came from. That's you. You're the result of billions of years of cosmic evolution. Not the end of the story, perhaps, but a luminous moment in it. A moment where the universe began asking itself questions. Where it began naming the stars, writing poetry, building machines to explore worlds it could never reach on foot. And in all this there is a quiet kind of power. Not the force of impact or heat or gravitational collapse, but the power to feel, to remember, to grieve and to laugh, to pass knowledge from one generation to the next, not through genes alone, but through language, through stories, through art, to say, I was here, I saw this, I tried to understand. No other known force can do this. Stars cannot reflect, black holes cannot recall, even galaxies, for all their grandeur, cannot compose lullabies or paint the way a summer evening feels, but you can, and the atoms that make this possible came from a place unimaginably distant, both in space and in time, It may be tempting to see this as a kind of accident, as a random flicker in a sea of cosmic indifference. But even randomness has beauty. And even a brief match flame flickering in wind changes the dark around it. Life is rare not because it is impossible, but because it takes patience. It takes timing. It takes stars to die, and planets to form, and oceans to stir, and chemistry to wander, just long enough to become biology. It takes billions of years for cells to learn how to talk to each other, to specialize, to organize, and one day, to wonder what they are, and here you are, a brief arrangement of particles, shaped by physics, animated by biology, and lifted, somehow, into awareness. You will not last forever. None of us will. But while you're here, you hold something that not even quasars or supernovae can claim: the ability to know that you are alive, to know that the universe is vast, to know that you are a part of it, and it a part of you. So as you drift off tonight, remember this: the stars that died to make you did not do so with intention, but from their ashes you emerged, and you do have intention. You can choose to create, to care, to learn, to leave something behind, not just in matter, but in meaning. You're not merely stardust, you're stardust that dreams. If you hold a pebble in your hand, it will not remember where it has been. The ocean may have tumbled it for centuries, worn it smooth with patient tides, and yet it carries no story. A tree, older than generations, may stand through storm and drought, but when it falls, it leaves no journal. The stars above, bright, ancient, enduring, do not keep a record of their light. But you remember. This too is power, not explosive, not gravitational, not even biological in the ordinary sense, but something else, something quieter, more persistent. Memory, the ability to take time which moves endlessly forward and carry pieces of it with you, to turn the past into presence, to let what once happened continue to shape what you do now. And that makes you, in a very real sense, a time traveller. You don't move through time any faster than anything else, but you can look back. You can replay what was. You can imagine what might be. And in doing so, you create something extraordinary, a life shaped not just by instinct or reaction, but by reflection. You become more than a process. You become a story. This capacity to reflect, to plan, to remember is what allows for civilization, for learning, for growth. Every book ever written, every song passed from one mouth to another, every idea that lingered long after its speaker was gone, all of it rests on memory. Not just the fragile memory inside the human brain, but the shared memory we build in language, in stone, in parchment and code and satellite signals. It is the storage of pattern, and pattern is what makes meaning last. Unlike physical forces, memory doesn't exert push or pull, but it rearranges. It allows knowledge to accumulate, generation by generation, idea by idea. In a universe where entropy, the tendency toward disorder, is always increasing, memory is a rebellion, a small act of order, a decision to keep something rather than let it scatter. Think of how much power that gives you, not just to survive, but to adapt, to notice that fire burns and teach your children how to carry it safely, to remember which plants heal and which harm, to understand the stars, not as mysterious lights, but as markers of seasons, of journeys, of myth and mathematics. You are not the strongest animal. You do not run fastest. You do not leap highest. And yet, here you are, mapping the cosmos, sending your voice across oceans of time. That is not force. That is intention, guided by memory. And memory, when shared, becomes culture. Civilization is not a structure of stone. It is not made of cities or borders or flags. It is made of ideas, delicate, powerful patterns passed hand to hand, mind to mind. ideas that shape laws, ideas that inspire compassion, ideas that spark resistance, renewal, understanding, and ideas do not obey gravity. They do not decay with half-lives or scatter like particles. They spread, and in spreading they change the shape of the world. An idea can cross oceans faster than ships. An idea can survive the burning of libraries, the fall of empires, the forgetting of names. It can rest silently in a book for centuries and then awaken, reshaping minds long after its creator is dust. In this way, consciousness extends beyond the individual. Your memory does not end at your skin. It continues in those you teach, in the marks you leave, in the kindness or courage that ripples outward from your life. This is not metaphor, it is thermodynamic fact. When you act, the universe changes even in small, invisible ways, and sometimes the smallest change is enough. This is why we speak of a different kind of power. Not brute force, but narrative force. The power to shape meaning. The power to take the raw, unfiltered flood of experience and make sense of it. To ask not just what happened, but what it meant. And to let that meaning guide what comes next. Every civilization is built on this. Not just the technology we create, but the stories we tell. About who we are, where we came from, what we value. The story shapes the structure. The myth becomes a map. The quiet, inward act of memory becomes the blueprint for action, for art, for empathy. And when you reflect, when you remember, when you change your mind, you are participating in this strange, vast collective unfolding. You're not only shaped by the universe, you are helping shape it in return. So let this be your quiet reminder tonight. The power to change is not reserved for the mighty. You carry it with you, in your thoughts, in your words, in the small decisions no one else sees. That is not a weakness. It is one of the rarest forms of agency we know. You may never collapse a star. You may never bend light or send gravity rippling through the cosmos, but you can remember, you can reflect, you can choose. And in a universe where most things simply follow the rules of motion, that is its own kind of miracle. You're not just a being shaped by the past, you are a shaper of futures. And so, we arrive at the quiet edge of wonder, not at the end of understanding, but at the soft pause where curiosity exhales. The stars above still shimmer, patient and unbothered by our questions. The atoms within you still hum their ancient tune, arranged in patterns older than memory. The universe continues its steady unfolding, not hurrying, not waiting, just being in perfect silence. You've walked far tonight, across the bridges of time and energy, through the strong force that binds the smallest pieces of existence together, through gravity's slow pull across galaxies and the invisible touch of dark matter holding everything in place. You've drifted through the dying cries of supernovae and the quiet birth of new stars, through the shadows of black holes and the soft breath of quantum fields. You've stood at the beginning, at that first moment of light, and followed the whisper that asks why there was something instead of nothing. And now the question returns, softly, as all great questions do: what is the most powerful force in the universe? At first it seemed a contest. Gravity against the strong force, energy against emptiness, matter against time, each immense, each beyond the reach of language. Yet as the noise fades, another truth begins to glow beneath it. Power was never about domination. It was never about who wins. Power, in its truest form, is harmony. The way everything fits together. The universe doesn't choose one force over another. It weaves them. The strong force holds atoms so gravity can sculpt stars. Electromagnetism paints their light across space. Dark energy stretches the stage so the dance can continue. None of them alone could make what you see tonight. The spiral of galaxies, the shimmer of oceans, the warmth of your own breath. Power, perhaps, is not a single note, but the melody formed when they all play together. And maybe, just maybe, the most powerful force is awareness itself. You. A spark of consciousness that can look into the dark and ask. The ability to see the pattern, to name it, to feel small and still keep wondering. You don't bend space-time or fuse elements, but you do something rarer. You find meaning. You create care. You imagine what the universe could be. Or perhaps the greatest force is the universe's own persistence. The quiet insistence to continue. To expand, to cool, to change and yet endure. The galaxies are not in a hurry. The stars do not compete. They simply go on, one pulse at a time. Maybe true power is not explosion, but endurance, the soft determination to exist. In the end, the answer may not be one force, one constant, or one name. It may be context, the relationships that make everything else possible, the way silence allows sound to exist, the way darkness makes the stars visible, the way you lying here belong to both, the stillness and the light. So, let the story rest now. You don't need to hold every idea or remember every fact. Let them drift, like starlight stretching into distance. What remains is the feeling that you're part of something vast, and yet it fits around you perfectly. You're small, but not unimportant. You're quiet, but not unseen. You're a single breath in an endless sky. And somehow that is enough. The universe is still here, still expanding, still making room for your thoughts, your questions, your dreams. Sleep now, little force in a great unfolding. The galaxies will keep turning while you rest. And when morning comes, the light that touches your face will be billions of years old. A gentle reminder that even across all of time, you are never far from the stars.